No. Okay, so again, like most of the kinds of functions that we study in here, there's always going to be one part which is about graphing the functions, another part which is about simplifying expressions, and then the last part which is about solving equations in some order. In this chapter, we do the first part is the graphing part. That's today. The next two lessons are about the simplifying. And when you have to simplify rational expressions, that's going to mean add, subtract, multiply, and divide. That's generally the hardest part of what we do in here, because that's, you know, if you're not good at adding and subtracting fractions of numbers, then what are you going to do when you get rational, you know, variable expressions involved? So that usually is the hard thing. So we take 2 days on that. It should have our quiz on the for us on the 12th. So by rational function, what we mean is a function that can be written as a fraction. And this is a pretty standard notation, which is to say, f of x is the rational function. It consists of a fraction which has a polynomial p of x in the numerator and q of x in the denominator. They always use p and q. Right, both of these are polynomials. Now, why does it say that at the end? Why does it say q of x does not equal 0? You cannot let the denominator equal 0 in a fraction. That's why. It's a domain statement, basically. Good. So examples of rational functions are like this, right? The first one, it's a linear polynomial divided by a linear polynomial. That's rational function, right? Or here's a quadratic divided by a quadratic. Now, in the last one, the h of x is a polynomial. Is a constant function a polynomial? Yes. When we did polynomials, constant functions can be. It's a horizontal line, but yeah, so the constant function can be a polynomial. Not good examples, because they really don't help us much. And you would say, well, if 1 over x is a rational function, then why wouldn't x over 1 be a rational function? And the only thing is, yeah, it is. Kind of it is. And sometimes the book homework problems, they include rational functions which actually have constants in the denominator. But in the end, that's a polynomial. I don't really need to use all these complex rules for rational functions because it's actually just a polynomial by itself. So it's much more interesting to us if there's a variable in the denominator than if there's a constant in the denominator. And this is not as written in the form of a rational function that we just showed, right? Because we said it has to be one polynomial in the numerator divided by one polynomial in the denominator. That's not what that is. That's two terms being added up. So it's not in the right form. Now, I could make it into a rational function by finding the common denominator between these two and adding them up. But as it's written, it's not a rational function. So there's going to be like one set of rules that we use today that it really needs to be a rational function where it's just one function in the numerator and one function in the denominator, not multiple terms being added up. Okay. So the graphs of rational functions, except for one exception, which is called an inverse variation, they have very irregular graphs. They don't have like one parent function and then we can just say, and now we'll move it all around by adding a number here and subtracting a number there, like we've done with all the other functions. The one exception is called an inverse variation. And that one you can. And so we're doing in two parts today. The first part of this, we will look at the graph of an inverse variation, and we'll transform it around just like we've done with all the other functions that we've dealt with. And then we'll deal with the graphs of all the other graphs of rational functions. And we really don't graph them, but we have to understand their characteristics anyways. Okay, good. Michelle? So an inverse variation is of the form y equals k divided by x. Honestly, I think you did some of this in Algebra 1. Do you remember doing this in Algebra 1? Inverse variation? I know like direct variation, that's definitely in Algebra 1, because the direct variation is a straight line. It's linear stuff, and that's Algebra 1. We don't even touch that here. So the form of a direct variation is y, or an inverse variation is y equals k divided by x. The k stands for the constant of variation. It is a constant, right? It's a number that we have to plug in eventually. It's not a variable. It's some fixed number. And k is definitely the letter that's used for the constant of variation every place that I've ever seen except for our textbook. Even the SOLs, as they're stated, they talk about k and the constant of variation. If you look at our book, they're going to use a. You know, in the end, it's constant, so it shouldn't make that much difference. So this is what we call inverse. The one that you've seen before, and ultimately we are responsible for doing more with this than we're going to do today. But I'm not going to do it now. I know I've seen the semester exam, and there's one question, and it really doesn't involve anything more than just recognizing what's a direct, what's inverse. Here's the other two, just so, and you may have already, I know you've seen inverse, right? Sorry, direct. Direct looks like, see if I got my blue going there. I think I do. Direct is y equals kx. So notice the difference between what's considered to be a direct variation and what's an inverse variation. In a direct variation, because y and x are both in the numerator, if I increase x, that's going to increase y. If I decrease x, that's going to decrease y. They're going to change in the same direction. But with an inverse variation, because actually the x is in the denominator, when I make the denominator of the fraction bigger, it makes the y smaller. Or if I make the x smaller, it'll make the fraction bigger and y bigger. So they're going to change in opposite directions. That's inverse. Direct, they change in the same direction, and inverse, they change in opposite directions. Now there's one other that we are required to know what it is, and that is called a joint variation. And that it looks like this, and you need another variable, k, x, y. So z is a variable. The joint variation, the variable z varies jointly with x and y. And just comparing it to the direct variation, why don't you just say it's direct? But you don't. When it's a direct variation with a product, it's called a joint variation. Now you can have all different combinations of these things. I'm pretty sure, because I asked the last class the same question, but you probably may not have seen this yet. Have you? Anybody in chemistry? If you're in chemistry and you haven't seen this, you will see that. Right? That's called the ideal gas law. And it tells you for a certain kind of a gas, the relationship between the pressure of the gas, the volume of the gas, the amount of the gas, and the temperature. All those four interact with each other. The R is actually the constant. It's like the K. Now, just to make it a little more interesting, right? PV, or I could solve for P, I would get nRT divided by D. And now I could say that the P is varying jointly with N and R and inversely with V. Right? That's a combination. So these are just the starting point is to understand what's inverse, direct, and joint. And then you can put them together in all different kinds of ways. Right? So in one of my past careers, right, I was a meteorologist, and we used the ideal gas law where the gas is the air. Right? So we were using this to come up with, intelligence about what's going on between the pressure and the volume and the temperature and all that stuff. In fact, we used it in a slightly different format, which I'm not going to show how we get there. But this is what we used more. Rho equals P over RT. So we introduced a different variable. That's a Greek letter, which is called rho, and that means density. You know what the density of something is? What does it mean if something has a high density? It's heavy, right? And something which has a low density, like cotton candy, is very light, right? For the amount of space that it occupies, it's very light. So we use this for air. That tells us something because rho and T, temperature, vary inversely. That means when the temperature gets warmer, when T gets bigger, what happens to the density? It goes down, right? Which means the air rises, right? When you warm things up, the density goes down, which means it gets lighter and it goes up. If the temperature goes down, right, gets colder, then the fraction gets smaller and the density is lower and things sink. So we kind of already kind of know that, right? Warm air rises, cold air sinks. That's why. And it's something that's pretty much, you're using our different variations like that. But we're more interested in the graphs today. So you got to start somewhere. And if you remember when we did exponential and logarithms, there has to be a base of those. The base, if it's 2 to the x or 3 to the x or 5 to the x, the 2 or the 3 or the 5 is not a transformation of the graph. It's just there's got to be a number in the place of the base. Well, when it comes to a direct or inverse variation, you got to have something in the place of the k. I can't graph y equals k over x. I can graph y equals 1 over x or 2 over x or 3 over x or whatever. So I'm just putting in a 1 for k so that I can graph it. Okay, and we'll see in the end that we're not really that interested in whether it's a 1 or a 2 or a 3. The graph is pretty much the same anyways. So here I've got my function y equals 1 over x, and I made a table of values. Because if you don't know what a graph looks like, plug in some numbers, see what it looks like. And I calculated all my y values, and I plotted them on a graph, and I connected all those points with lines. Now, again, why does it say x does not equal 0? Because you can't divide by 0, right? Well, if x cannot equal 0, that means the graph cannot cross the y-axis, which means the y-axis is what? It's an asymptote, right? The graph cannot cross the y-axis. Therefore, it has a vertical asymptote on the y-axis, x equals 0, which means as I plug in all these values of x here, I'm going to get some values that are less than 0 and some x values that are greater than 0, but they can't be connected. I can't draw a line that connects these two. It's going to be two distinct portions of the graph called branches. Right, here's one branch, here's another branch. Right, it's discontinuous because if I wanted to draw it, I would have to draw one branch, pick up my pencil, move it to the other, draw the other branch. Right, polynomials aren't like that. Polynomials have smooth, continuous graphs. But a rational function is not. It's discontinuous. So because of that, x does not equal 0. We've got a vertical asymptote. Okay. Now, is there any value we could plug in for the x here that would make the y equal 0? How can you make a fraction equal 0? Which part of the fraction has to be 0? The numerator has to be 0 for a fraction to equal 0. But the numerator is a 1. It's clearly not 0. So there's nothing we can do to make this thing equal 0, which means the graph is actually never going to touch the x-axis either. So it has a horizontal asymptote, y equals 0. So we've had horizontal vertical asymptotes before, but we never had both in the same. And that's what rational functions have. They've got both vertical and horizontal asymptotes, or at least both are possible all the time. Now, if there's a vertical asymptote on the x-axis, which is x equals 0, that means the domain is x does not equal 0. That's the one value that x cannot have, that you cannot plug in. And since y will never equal 0, the range is y does not equal 0. So those are the basics of the graph of an inverse variation. Now, the next couple slides, just a second. Okay. I'm going to show that if I compare 1 over x to 2 over x, I mean, it clearly changes the graph a little bit, but it's still essentially the same shape. It still has asymptotes on the y-axis, on the x-axis. The graph still is in quadrant 1 and quadrant 3, and it's veering off towards the asymptotes on both sides. The domain and range would be the same. So for us, it doesn't make a lot of difference what the constant in the numerator is. For all the things we're really looking to get out of these, it's the same. Domain, range, asymptotes, the basic shape. Good, Emily? And the other one I want to show is what happens usually when we put a negative in front of the function. What does it do to the graph of the function? It flips it, right? So in this case, if I compare 1 over x to negative 1 over x, right? Here's the 1 over x, quadrants 1 and 3. If I put a negative in front of it, it takes that from the first quadrant, it flips it to the fourth quadrant. It takes what was in the third quadrant, it flips it to the second quadrant. Right? So these two are positive inverse variation. These two are negative inverse variation. So with all of that, now we can do what we've done before. We can shift these things around by adding and subtracting inside and after the function. So now, what would we expect to be the result of adding 2 inside of the function? Based on what we've done before, is it up, down, left, or right? Left 2. And what's the effect of subtracting 1 after the function? down 1. Okay, so we would expect in this one that we're going to have the basic shape of an inverse variation. It's going to be scooted 2 to the left and 1 down. And then what is going to be the effect of the negative in front of that? It's going to flip it. It won't be in 1 and 3. It's going to be in 2 and 4. So when you sketch these graphs, the first thing you got to do is you got to get the asymptotes in the right place. Right? So if the whole graph is being shifted 2 to the left, that means the vertical asymptote is going to be 2 to the left. So I've got to do this. 2 to the left. There's my new vertical asymptote. And then the horizontal asymptote, if the whole graph has moved 1 down, then the horizontal asymptote has moved 1 down. That's about like right there. And we said it's going to be in quadrants 2 and 4 because of the negative. Now remember, the quadrants are not determined by the x and the y axis. They're determined by your asymptotes. So we're going to sketch, and there's a reason I use a word sketch and not just say graph, because we're not going to plot points. All we're going to do is put those 2 branches roughly where they belong, and that's enough. Okay? So don't use this to guide your drawing. Use this. Right? And since it's a negative, we're not going to draw it here and here. We're going to draw it here and here. So just freehand in 2 branches that'll look something like this. There you go. Oh, I did that in exactly the wrong spots too, didn't I? I got to do that again. Edit, undo, edit, undo. And mess that up completely. Is it letting me do that? I don't think so. Darn it. Try to erase it. That should have been in 2 and 4, and I just went ahead and did it in 1 and 3. And if I do this, it's going to mess me up a little bit. That's okay. So I should have made it in 2 and 4. What is the domain? Remember, if this is the vertical asymptote, x equals -2. This is the horizontal asymptote, y equals -1. What is the domain? What's the 1x value that cannot be in the domain? -2. So you have to say x does not equal -2. And what is the 1y value that will not be in this one? Y does not equal -1. Like that. So you don't have to plot points. Just sketch an approximate shape. So what are the shifts in this one? 5 down. Remember, it's left and right when it's inside the function. So this -5 here means down. So I definitely need to move the asymptote down 5. 1, 2, 3, 4, 5, about right there. Okay, what about the vertical asymptote? Where is that going to go? It's still at 0, right? Didn't move. There's no shift horizontally. So we're still going to go like this. Okay, and now which 2 quadrants should I draw this in? Should it be in 1 and 3 or 2 and 4? How do you determine which one? If it's negative, right, in front of the fraction, then it should be 2 and 4. What about this one? It's positive, so it should be 1 and 3. So just sketch the approximate shape in here. Should be something like that. What is the domain? What is the domain? Y does not equal -5. Piece of cake. So do that one for yourself. Somebody got something close to that? Except for my terrible graphs. Okay. So now we're going to move on to not graphing the other rational functions, but just understanding what we can understand about them. And the things that we should be able to determine about the equation of a rational function are, we should be able to find the zeros. By zeros, I mean where it's across the x-axis. We should be able to tell where the horizontal and vertical asymptotes are. We should be able to tell the domain, because the domain and the vertical asymptotes kind of go together. And the end behavior. Do you remember when we did end behavior before? Right. End behavior with polynomials, if you remember, looks something like this. You know, we would say as x approaches positive infinity, it looks like y approaches positive infinity. As x approaches negative infinity, it looks like y approaches negative infinity. Those are the kind of answers that we got for that. But now, we're going to have horizontal asymptotes on the graph. And that means that the graph is actually not going to approach infinity or negative infinity. It's going to approach whatever the y value is on the horizontal asymptote. Right. When there is a horizontal asymptote, which is not always, but when there is, then we'll have a different kind of end behavior than we've seen before. So we're going to go through one by one. How do you find these things, right? How do you find the zeros of a rational function? Well, again, if a fraction equals 0, it's because the numerator equals 0. So you look for the zeros of the numerator. Whatever the zeros of the numerator are, those are the zeros of the function. Okay. Next. The vertical asymptotes of the function are x equals, right, because it's a vertical line, it's x equals the zeros of the denominator. Right? It's x equals whatever makes you divide by 0. Can't let that happen, so those are vertical asymptotes. Okay, the domain, once you figured out what the vertical asymptotes are, the domain is x does not equal the zeros of the denominator. Alrighty? And then horizontal asymptotes, there's 3 rules. And the 3 rules, which there's only 2 on this slide, but the 3 rules are based on the degree of the numerator and the degree of the denominator. What do we mean by the degree of a polynomial? Got to know this word. The degree means the highest power of x. So you're going to compare which has a higher power of x, the numerator or the denominator. The first case is what happens if the degree of the numerator is less than the degree of the denominator. Something like 1 over x. There's more x's in the denominator than in the numerator, so that would tell you the degree is greater in the denominator. Okay. When that's the case, then y equals 0. That is a horizontal line right on the x-axis. That's the horizontal asymptote. Right? Whenever the power of the denominator is more than the power of the numerator, y equals 0. If the degree of the numerator is more than the degree of the denominator, then it's like this. This is a simple example. But since the x squared is a higher degree than x to the first, then there is none. I mean, this you could simplify. That's y equals x. Right? Y equals x is a straight line. That doesn't approach some fixed value. It's going towards infinity or negative infinity. Right? So the first 2 rules are, when the numerator has a higher degree, there is no horizontal asymptote. When the denominator has a higher degree, then y equals 0 is the horizontal asymptote. Just like we saw. I mean, this is an inverse variation. We saw that one already, right? It had an asymptote at y equals 0. So what's the one situation that's not described by either one of those 2? What if the degrees are equal, right? If the degrees are equal, then we've got one more rule. Wait for everybody to catch up. Sarah, good. Priyashi, you good? Okay. And we need just a little more information then, right? So if you have a polynomial in the numerator and a polynomial in the denominator, if the degrees, the n and the m, are the same, then it'll be y equals the ratio of the coefficients of the leading terms. Y equals a over b. So it's all based on degrees of the numerator, degrees of the denominator. You know, something like, you know, if f of x equals 2x to the third plus dot, 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 divided by 3x to the third plus dot, 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 for more terms, then the horizontal asymptote is y equals 2/3. It's the ratio of the coefficients of the leading term, or the highest degree terms. So if we were going to graph these, we would go to our graph, right, and draw at y equals 2/3, make a dashed red line or a dashed line, and use that as a guide for drawing what's going on the ends. So that leads to the end behavior then is, if there is a horizontal asymptote, then the end behavior of the graph is that the function is approaching that value, whatever it is, right? If the asymptote is y equals 0, that means the end behavior is y approaches 0. If the asymptote is y equals a over b, then as x approaches infinity, f of x, or y, is approaching a over b. Right? It has to be getting infinitely close to that line without touching it. It must be said that there's a fundamental difference between a vertical and a horizontal asymptote. A vertical asymptote, because that value of x is not in the domain, the function cannot cross that asymptote. Never, ever. Okay. A horizontal asymptote is not a line that the graph can't cross. It's a line that the graph will approach as x approaches positive and negative infinity. It'll actually cross the horizontal asymptote when x is small. Sometimes around the middle of the graph, it's common to see it cross the horizontal asymptote. But that's what it's describing, what's going on at the ends of the graph. That was wrong. So well, I'm going to go through a few problems like this, which are going to be like your homework problems too, right? So we're going to, on the homework problems, because they're not what the book tells you to do in their homework problems, but you're going to use their problems and just do what we're doing right here, exactly what we're doing. So we're going to go through this list: zeros, vertical asymptotes, horizontal asymptote, domain, and then behavior. So why does it say vertical asymptote with an S possible at the end and a horizontal asymptote? No. I mean, if you put an S, it means you could have more than one, right? Can you have more than one vertical asymptote on a graph? The answer is yes. Could you have more than one horizontal asymptote? Meaning, could there be two values that the graph is approaching as x approaches infinity? No. If it did, maybe that would look like something like this, right? If I've got an asymptote here and an asymptote here, and it's approaching both, right? Then, maybe it's connected like this. Is it a function? No, it's not a function, right? It wouldn't be a function if it had two horizontal asymptotes on it. So that is not a case that we're ever going to see, right? So you can have one horizontal asymptote. You could have more than one vertical asymptote. Okay, let's start with zeros. How do you find the zeros again? The zeros of the function are the zeros of the numerator. Okay, what are the zeros of the numerator in this case? Can that numerator ever equal 0? What is the value of that numerator? It's 5, no matter what. There are no zeros. Is there any variable you could plug in for? No, there are no zeros, right? So you say none. Okay, vertical asymptotes. How do we find vertical asymptotes? The zeros of the denominator, right? Well, it usually helps in these problems, and today a little bit, and in the next few lessons, really a lot, factor. If there's something to factor, factor it. Luckily, most of the time, they give us fairly easy factoring problems. Like this one should be fairly easy. X plus 1 times x minus 1. It's a difference of squares. Okay, so now if I say the vertical asymptotes are x equals the zeros of the denominator, what are those two lines? X equals -1, x equals 1. Okay, and you can't just say 1 and -1. If you don't have x equals, it's not a vertical line. So you got to include that. Now, what is the domain? What does it say in the instructions I gave you? How do you find the domain of the function? X does not equal the zeros of the denominator. So you just take this and say x does not equal -1 or 1. Okay, horizontal asymptote. So using our 3 rules, right? Which has a higher power, denominator or numerator? Denominator has the higher degree. So according to the rule, when the denominator is the higher degree, the asymptote is y equals 0, right? Make sure you don't just say 0. It's got to be y equals. And that, what does that make the end behavior? as x approaches plus or minus infinity, y is approaching 0. Whatever the horizontal asymptote is, that's what it's approaching. Good. Sydney, okay? Bending. Okay, same thing. Zeros. The zeros of the function are the zeros of the numerator. Okay, what's the zero of that numerator? -1. X equals -1. That's the x-intercept, right? The vertical asymptotes. The vertical asymptotes are x equals the zeros of the denominator. What are the zeros of the denominator? If you plug in 5 or -5, what is 5 squared or -5 squared? 25, right? 25 plus 5 does not equal 0. I mean, if you have to, set it equal to 0 and solve. What kind of a number are we going to get when we square root -5? It's non-real, which means it doesn't show up on our graph. There is none. Right? So when there are no real zeros of the denominator, that means you got no vertical asymptotes. Okay, and domain. Remember, the domain was supposed to be x does not equal the zeros of the denominator, but there are no zeros of the denominator, so what does that make the domain? All real numbers. You can plug in anything. And the horizontal asymptote, by the rules, it should be like the last one, right? The higher power is in the denominator, so it's y equals 0. So that makes the end behavior as x approaches plus or minus infinity, which means as you go to the extreme left of the graph and the extreme right of the graph, the y values are approaching 0. Right? These two match. I think the next one will be for you guys here. So try to do that one. Okay. So how did the denominator factor? Okay, well, then what is it? What are the factors? I'm not hearing yet. What is the factoring of the denominator? X plus 3 times x minus 5, right? What were the zeros? the zeros of the function. Okay, -3. If you plug in -3, right, -3 squared is 9. 9 plus 9 is not 0. There are none, right? You got to recognize that in this kind of a thing, when it's x squared plus a number like it was in the denominator of the last one, that's never going to equal 0, because the x squared is always positive and the 9 is positive, so there's no way for that to equal 0, right? So it should have been the zeros were none. The vertical asymptotes were the x equals the zeros of the denominator, which were x equals 5 and x equals -3, which makes the domain x does not equal 5, x does not equal -3, right? Now, this one, by the 3 rules for horizontal asymptotes, because the degrees of the numerator and denominator are the same, it should be y equals the ratio of the coefficients of the highest degree terms, y equals 1, which makes the end behavior, as x approaches plus and minus infinity, then y approaches 1, whatever that value is. We're good? Okay, try that one. So how did the numerator factor? Again? X minus 12, x plus 5, right? And what did that make the zeros of the function? 12 and -5, right? The vertical asymptote is x equals -3, the 0 of the denominator. That makes the domain x does not equal -3. And the horizontal asymptote, again, by the rules, when the numerator has a higher degree than the denominator, what's the rule say? There is none, right? So there's none, which means the end behavior, and this is enough for what we're doing right now, is y is going to positive or negative infinity. It's not approaching some fixed number. Good. Taylor. Emily. Okay. Now, if I'm going to factor this, how does the denominator factor? You know, most of the time you're going to be given, there's going to be factoring to do, especially in the next couple lessons. There's always factoring to do. But, you know, most of it is usually the easy kind of factoring, I hope. I mean, what kind of factoring would you do in the denominator there? Greatest common factor? If you can't think of anything else, just see, is there a common factor between those two terms? What is it? X. So take out an X. That'll help. And what about the numerator? Is that any kind of pattern that we've seen? It's the sum of cubes, right? You got to, that 27 should just be kind of blaring out at you, you know. That's a cube, x to the third. This is the sum of cubes, right? That's why we learned those. So that would factor like this: x plus 3 times x squared minus 3x plus 9. Okay. Okay, what are the zeros of the function? The zeros of the function are the zeros of the numerator. What's 1 0 of the numerator? X equals negative 3. Okay. What about the x squared minus 3x plus 9? If you remember, when we did polynomials, if we had to solve a polynomial equation that was the sum or difference of cubes, you got a real solution from the binomial, but it's always imaginary solutions. There's no more factoring you can do, and if you try to solve it with quadratic formula, you get imaginary, and we're not interested in imaginary. So the only zero of the numerator is negative 3, right? How about the vertical asymptotes? It should be x equals the zeros of the denominator. What are the zeros of the denominator? 0 and negative 3. So x equals 0, x equals negative 3. What does that make the domain? X does not equal 0 or negative 3. Right? What is the horizontal asymptote? None, because x to the third over x squared. And that makes the end behavior y is approaching plus or minus infinity. Now there's something wrong with that, isn't there? How could it be that negative 3 is a zero of the function if it's actually a vertical asymptote of the function? So that brings up a particular case that if you have an x value, which it's coming from a factor which is actually shared by the numerator and denominator, the fact is, I mean, you could cancel those two, right? They would just cancel the x plus 3s. They don't need to be a part of this graph at all. But what it means is at x equals negative 3, you don't have a vertical asymptote, right? A vertical asymptote is a very particular thing. It means that the function is like veering off towards infinity or negative infinity as it approaches. That's not what happens at x equals negative 3. At x equals negative 3, it does this. In fact, here's the x equals 0, right? There's a vertical asymptote there, and you can see the graph is veering off towards infinity on both sides of it. But here, there's actually like a little open circle on the graph. The graph is not defined for x equals negative 3, but it's not veering off towards infinity. In fact, it's just jumping over that point, one point. If you had it in your calculator, you wouldn't even be able to see it, but you'd see it in the table of values, but you wouldn't be able to see it on the graph because it's so small. That's called a hole. So usually what you look for are the zeros of the denominator, and then you say, and these are the vertical asymptotes, and these are the holes. But they don't actually ask us in Algebra 2 about the holes. It should not come up that you have any holes in the graph. Everything should be a vertical asymptote. But if it does, that's why it is. Right? It looks different on the graph. When you get into, you will actually graph these things in math analysis. You'll have to like plot points and draw in everything. And then you'll draw in the hole if there is one. Okay. And then there's one other I was going to show, and then that's it, which is most of the time the factoring will be easy. But if the factoring gets hard, it's going to be hard like this. It's going to be something which is like a quadratic, which is not the simple quadratic. Do you remember how to factor something like the numerator of that fraction? What are the steps? Right. 2 times negative 20 is negative 40. What are the factors of negative 40 that add up to negative 3? Negative 8, positive 5, right? So what do we do with that? We split up the middle term, so it's 2x squared minus 8x plus 5x minus 20. That was not the 20. Minus 20. We group the first two terms. The first two, we group the last two. We factor each set of parentheses, greatest common factor, 2x times x minus 4, plus 5 times x minus 4. And last step, 2x plus 5 times x minus 4. Most of the rest of the factorings will either be simple quadratic or greatest common factor or difference of squares. It's rare to have something much more than that, but if it is, it's something like this. Okay, so now, what are the zeros of this function? Here's the factored form of the numerator. What are the zeros? 4 and negative 5 halves, right? 2 times negative 5 halves plus 5. Okay, vertical asymptotes. What are the zeros of the denominator? Again, it's that same pattern, x squared plus 1. What are the zeros? Emma? What's that? There aren't any. None. Good. Which means the domain is all reals. The horizontal asymptote is say it, y equals 2, right? Which makes the end behavior, right, as x approaches plus and minus infinity, y approaches 2, right? These are the same. All right. That's the homework. And again, for the homework, follow these directions for these problems, right? It's just what we did on all of those.